Welcome back. Let's consider an example. Okay, let's construct a distribution and see how things work. So let's say that assume that, let's take an example. Suppose x is in R and y also is in R, because I cannot draw anything if it's more than R. Okay, so I'll take both of them in R, and let's say that this is how I define my distributions. Y is equal to some ax squared plus b plus epsilon. Epsilon is Gaussian 0 1, and a and b are some numbers. See what's happening, my pxy, what distribution is pxy now? It's Gaussian, right, with a particular mean and variance. So the reason I did it this way is I just wanted to draw the data. Come again? I is a 1 by 1 matrix. Okay, let me draw that data. No, okay, these are my data points. How many of them do I have? So this is x and this is y, and we have 1 2 3 4 5 6 7 8 9 10. Okay, 10 data points. I'll tell you why I counted that in a while. There are 10 data points in my data set. Okay, and this is how it is. See, some textbooks tells you that okay, I mean, there's a parabola and you just perturb it and you add noise to it to get data. I mean, all that I'm doing is I'm generating a data from an underlying distribution that is Gaussian. That's it. The reason I did it this way is that I can write it around a particular parabola. I mean, this dotted line has no significance whatsoever. And I think all of you understand that, because we are looking at a probabilistic way of looking at treating things. Okay, this is what my data is. Okay, am I overloading notations here? See, these x's are yeah, maybe I'll change it. What symbol do I use? Circles is not taken. Don't think that they are zeros or something. No. Okay, okay. 1 2 3 4 5 6 7 8 9 10 11. I have 11 now. Okay, make it 10 easy that way. Okay, this is the data set that I have. Now let us compute. Let's say that we are solving an ERM problem with squared error loss. Okay, I will write two classifiers or two regressor, two hypotheses, and let's study what will happen to bias and variance. Okay, the first classifier is, the first regressor is, let's call that h1 of x. This is equal to 2 for all x. This is one classifier. Okay, there is another classifier, h2 of x is equal to y for all x. H of xi is equal to yi. So do you understand what these classifiers are? The first classifier is, or okay, it's a regressor. The first regressor or first hypothesis is that it's a constant for all data points. The second regressor is, it is equal to the particular y at all data points. What is it, by the way, this H2? Yeah, it's called lookup table. No, it's a lookup table. Simply a lookup table, right? I mean, you have given 10 data points, remember all those data points perfectly. Okay. Now, which one do you think is a good hypothesis? Huh? Neither, right? Yeah, so that's exactly the point. Neither of these are good hypotheses. Why? Let's look at this. What happens to the bias of the first one and variance of first one? Let's write that. So what about the bias of this and variance of this? What will be the bias of this first classifier? No, let's only say whether it's like high bias or low bias, right? What is the bias of this? Extremely high bias, right? What about variance? Please show this algebraically. Another homework. Show that for this particular hypothesis, variance is 0. Intuitively, why is the variance 0 for this? See, what is variance? Variance studies what is the variability across different samples of data set. This guy is not even looking at data. What variance? No variance. You take this person anywhere, he has very high head and he has his bias very nicely stitched completely, right? So no variance at all. Wherever you take them, they behave the same because they are completely oblivious to data, no? They are blind basically. We don't want such people, too much bias, okay? Okay, what about the second person, right? Second hypothesis. So let's write down the bias and variance for this. What's the bias of the second hypothesis? Yeah, please show that. This can be algebraically shown. This has zero bias. Why? Because what is bias? Bias is the deviation of the classifier from the reality. This is exactly the classifier on the data that it has been shown. What about the variance of this? Extremely high. So this is that person that adapts to the local environment too well. Okay, so has no opinion of his own. Very dangerous people. No? Both kinds of people are dangerous. We don't want people who are too high headed or the ones who gets adapted very easily. Okay, now suppose you have one side point is, suppose you have access to the entire universe and you build a zero bias classifier. ML is solved, right? My opinion is maybe that's what is happening in today's ML. You take the entire universe and remember it all. Okay, anyway, so that's an opinion. You can ignore the opinion, but here is the takeaway. The key takeaway is, okay, so tell me what happens to the accuracy of the second hypothesis, the training accuracy of second hypothesis. 100%. So here is the key punchline, right? Getting 100% accuracy on training data does not mean anything. Okay, because this, I mean, it may only mean that you might have ended up with a hypothesis that has zero bias with a very high variance. That's it. Make sense? Okay, so remember that. So what about the second case? Second case, it will have very low training accuracy, not zero. I mean, maybe you are lucky and some of the points are coinciding with this, right? But still, yeah, so it will have a large training accuracy, but most often what happens is you will end up having the second type of classifier or hypothesis where you get, because you are optimizing for training accuracy. You see, when you solve ERM, because you are doing it on D train, you are optimizing for training accuracy, and getting 100% training accuracy does not mean anything. Okay, okay, so now, so I'll come to it. Pragmatic way of trading. So typically in a small sample case, I'll take your question in a while. Typically in a small sample setting, the following behavior is observed. See, this is not, whatever I am saying right now is only empirical. There is no theory to it. Theory only says that the risk decomposes into these two terms. Typically in practice, whenever you are looking at small sample cases, this particular behavior is seen. Okay, what is that? Suppose you plot some performance metric along y-axis. It's plot error, okay. Generally 1 minus performance is what is plotted, 1 minus accuracy, okay. Along y-axis you take model complexity. See, what do I mean by model complexity? suppose we are looking at polynomial regressors, okay. The degree of polynomial that we consider as our hypothesis function can be looked into as model complexity. That is one way to measure model complexity. Now, the reason I looked at counted these points here is, suppose I take a 10th degree polynomial and try to do ERM on this, I can always find coefficients such that I get 100% accuracy on this, right? Because all points have one coefficient corresponding to each point. I mean, this is the extreme case in which I remember the data point itself. Instead of remembering the data point, you can have 10 unique numbers which are the coefficients of the polynomial, and associate each of them with one data point, and you get 100% tiling accuracy. So x-axis is that. So we are, suppose if we are considering polynomial regression, which is the generalized linear regression case, then x-axis is the degree of polynomial. As we move on in the course, this can be the number of layers in a neural network. Basically, it's the number of parameters that we have in model, right? Or it can also be, I mean, I told you that the models in which analytical differentiation of ERM is difficult, we will resort to the iterative way or numerical way of solving it, right? This x-axis may be different steps in your iteration. See, every step in your iteration actually gives you a different model if you look at it. Why? Suppose you are doing a logistic regressor, right? Every step in gradient is giving you a new set of parameters, which means a new hypothesis anyway. So that's x-axis. Okay. In neural network, what happens is, as you are doing that iterative gradient descent, every step will be plotted along x-axis. Do you see the point? If you do EM, then every step in EM is along your x-axis. It's a different set of parameter, and I'm assuming that as I'm going from left to right, the complexity of the model is increasing. That's an assumption. I choose to plot the graph that way. It doesn't have to be the case, but typically it happens that way. Because as I said, right, if you are doing a polynomial regression, you keep on increasing the order degree of the polynomial, then the complexity keeps increasing. Okay. Or if you keep on increasing the layers of a neural network, then it increases, and if you keep doing the gradient descent, it increases, is the assumption that have been made. Do you understand what x-axis is now? And this plot is common across all the hypotheses that we will see in this entire course. It has, and it's very general that way. Okay. Y-axis, we plot the error. Now, typically observed behavior is, okay, as the model complexity increases, so you start with a large error model because you have made some initialization. As the model complexity increases, the error keeps decreasing. This. So this is a typical behavior, okay. If you actually do it in practice, you don't see a curve that is as smooth as this. You will see something similar, not something exactly this. This is exaggeration, okay. Yeah. What is this? This is the risk or error on training data. Okay. Now, what happens to the validation data or test data or another sample of data set, right? What happens is, note that you are solving ERM on this D-train, and you are measuring your performance on some other data. It can be validation data, test data, anything. How does that look like? It looks like this. It will start decreasing and then starts increasing. So this is what is happening here. So this is the point where we want to ideally operate, right? Okay, each of these is taken as a different tick. Okay, this is the point where we want to ideally operate. So now what is happening? Why is this behavior seen? See, what happens is the following. This particular region, let's write down the bias and variance here. This is bias and variance. This is bias and variance. So what can you say about the bias and variance in the left part of this dotted line? This model is very high bias, low variance, right? And this is low bias and high variance, the two extremes that we saw. Okay, the H1 and H2, those two classifiers that we saw, one falls in the region of high bias and low variance, the other is in the region of low bias and high variance. We need neither. Okay, now this is the typical behavior. As I said, when the model complexity keeps increasing, the error or the accuracy on training data keeps decreasing, right? Because the more and more parameters that one is given, what is the intuition behind it? The more and more one is given the parameters, you can create a lookup table that would remember the entire data set, right? That's why you enter a low bias and high variance region. In the initial parts, what happens is, why the bias is higher is because the model is not capable of even explaining the seen data. I mean, forget about looking at the unseen data. So first you have to explain the unseen. Okay, this is how it is. You have to avoid both, but you need to operate at a place where both bias and variance are low. And in the popular culture, these two things are actually called something. Now this is called overfitting. The low bias and high variance operating point is called overfitting, and high bias and low variance point is called the underfitting. A hypothesis that has high bias and low variance is called, is referred to as one that has underfit the data, and the one that has low bias and high variance is referred to as the one that has overfit the data. Is that okay? Now here is a suggestion. If you are given an ML task to solve, okay, start by overfitting. You should at least overfit. Yeah. See, if you tell me that I am building a classifier that is not giving me 100% accuracy on even training data, then you have not even started ML. Okay, I tell this to all of my students that given an ML problem, start by overfitting. At least overfit and come back. What I am saying is, operate here. Okay, don't operate here. You can always come up with a classifier that can operate here at the region of low bias and high variance. And that is what is done in practice. In practice, what is done is, you always start with a classifier, okay, over parameterize it and operate in the region of low bias and high variance, and then push it backwards. And this process of pushing a hypothesis from the low bias and high variance region to a low bias and low variance region is called regularization, and that has exactly one-to-one correspondence with the Bayesian map estimates that we saw, which is what we will see later. So pragmatic analysis is that you always start, whenever you are given an ML problem, you always start at the region of low bias and high variance. How do you do that? You do this by over parameterizing the hypothesis. Is that okay? Yeah, let me write that. So tip, always start with a hypothesis that operates at in the low bias and high variance region. It's called the overfit region, and then push back, or rather region, by over parameterizing, right, via over parameterization. I can never accept an underfit classifier as an answer. Never. I mean, you tell me that I am getting 100% accuracy on training data and very bad performance on test data, I am fine. At least you have overfit. Okay, always start by overfitting and then push it back. This is how you do it pragmatically. I'll stop here for a while and take questions if there are any before we move on to the next topic. As I said, no, this is actually a very central part. Unless you have access to infinite data sets, okay, and a hugely over parameterized model, you will always end up with this particular type of scenario where you do very well on training data and pretty bad on test data, okay, because it's very easy to operate at the region of low bias and high variance by over parameterizing. Questions on this? Yes. I did not understand in the earlier example, why does the second hypothesis function of h2 x equals y, how does it have high variance? The 10 points that we have, they come from a single data set, and variance gives us how this changes with different data sets. How did we conclude that this changes? Okay. The question is how is the second hypothesis here has high variance? The variance term has an outer expectation with respect to PD as well, right? So we looked at one data set. Now suppose instead of sampling these 10 data points, I sample 10 more data points and plot them. What will happen to the error of the variance part of that classifier, this particular classifier? When I say yi, I am not changing yi per data set. That's what the confusion is. That's not what I am doing. I am making this equal to yi only for this particular data set, and even for the new data points that I have, right? Either this is not defined or it will give you a constant value. The question that you should be asking is, how would this classifier behave on some other data set? I have not defined it actually. The way to define it is, it only knows this many data points. When the new data point comes in, either it will give you a constant value or it will just randomly choose from one of this and then outputs, in which case the variance is too high. I think that was the missing piece. Did all of you get that? I think that's, I should say, for all xi in D, okay, and it's equal to h2 of xi is equal to anything, right? So 0 otherwise. See, this part I can do it anything, right? Because it doesn't know what to do when it is shown something outside of what it has seen. I can't stop myself from saying this when I started teaching at IIT Delhi, right? So a student of mine was telling him that, guys, I had a lot of expectations from you, and you people did not match my expectation. I was just having a private conversation. The guy said, I had just taught them, bias variance decomposition and all that. Sir, we are all models that have been overfit in quota for 2 years. That's exactly was his statement. You understand what it means? Most of these JE coachings happen in this place called quota, right? So it's severe overfitting over 2 years is what we have done, is what he was saying, right? So basically the idea is that an overfit model knows perfectly what to do when it is shown something that it knows. It has no idea what to do when it is shown something that it is not seen, right? So you need a balance, and it becomes too much of philosophy, but nevertheless, right? Everything needs a balance. You should have biases, right? And an ideal situation is that where you have zero bias and zero variance, right? And you quickly adapt. You get a new data set, immediately adapt, and you are so generalized that you can do it. It's very hard, but striking a balance between good biases and less variances is how one should operate. Anything else? Any other question? Yeah. Yeah. So the question is, why is it pragmatically? I did not say wrong. I mean, it's a typical way to do it is start from over parameterized model and reduce the parameters, right? It's because the only thing is it's functional ease. See, what happens is that if you start from an underparameterized model, right, you don't even know whether okay, you will know that that underparameterized model is not even explaining your scene data. Now you go till explaining your scene data, but where do you stop? The question is, where do you stop? On the other hand, if you start from completely explaining the scene data and pull it back till the point where it does well on the unseen data, I think that's a better strategy. It's only an engineering pragmatic strategy, nothing theoretically sacrosanct about it. In fact, as we will see in the next class, there are these methods called regularization methods, okay, which would give you a way to reduce the bias. It is easy to increase the bias. Yeah, increase the bias. it's easier pragmatically to increase the bias of a model. So you start from an over parameterized model that has very less bias and add regularizers to increase the bias. Pragmatically easier. You always over parameterize, overfit, and then increase the bias. No. Start from an over parameterized model that overfits, no? And then increase the bias. Not necessarily. See, we'll see that in the next class, right? When we look at regularization, the way we do it, no, we modify the empirical risk objective itself so that implicitly it has a high bias component to it. We'll see that. They are called regularizers. Yeah. Hold on, huh? Just to complete his question, right? If you people can see, whatever I am saying techniques as the ones that would increase the bias are very similar to the case where we imposed our belief on the estimation problem, isn't it? That's exactly what it is. See, I told you that ERM has a exact relationship or one-to-one relationship with ML estimation. Now regularized ERM has one-on-one relationship with the map estimator. They are exactly the same. So what we do is whatever bias that we have about the parameters, we impose them as regularizer, explicit regularizers. Basically, you people would have already guessed it now, right? We solve a constraint optimization problem. Instead of solving, see, ERM is an unconstrained optimization problem, right? Instead of solving an unconstrained optimization problem, you solve a constrained optimization problem and construct Lagrangians, right? Those constraints will be the Bayesian priors that you impose on your ML estimation. That's all. They are exactly the same. Right? So that's why it's convenient to impose our bias. Okay, it's not convenient to start from a very low bias model, because the least that we should do is explain whatever we are seeing right now. Okay. What is H bar? The question is what is H bar? H bar is not the same classifier. Okay, whenever you say classifier, you should know that it's a hypothesis. It can be classifier, regress, or anything. Yeah, it's not the same hypothesis that is performed, that is trained across different data sets. It's the average of those different hypotheses trained on different data sets. Yeah, when you say same classifier, it's from the same class of hypothesis. If you are looking at linear hypothesis, then you are looking at average linear hypothesis and so on. Yeah. Nothing. See, test data leakage is a pragmatic scenario, right? You should not do it. If you do it, then what people do is, if there is test data leakage, you always look at your test data and tweak your. See, the worst case scenario is that you train on test data. See, nowadays there are benchmarks that are being published, right, left and center. Every new model that comes up in the market, you'll have to show that you beat the new model, you beat the existing models. Now the best way to do that, or the worst way to do that, is to train on test data. Everybody has access to test data. Now how do you trust whether somebody has trained on test data or not? Typically what is done in global competitions, etc., is test data is like held out, it is not shown. But the worst way to do it is that include your test data and overfit on test data. Some of my students, if you were to cheat, right, some of my students are actually doing deliberately bad on test data, train on test data, so that you don't show 100% accuracy, you show 91.2% accuracy or whatever, right? So that's the worst thing to do. The second worst thing to do, right, is that you don't train on test data, but you set your hyperparameters based on test data. Right? For instance, you train a classifier, see what your accuracy is on test data, not on validation data. See it on test data. It's bad. Go back and change your hyperparameters. You are not training on test data, but you are changing your hyperparameters on test data. Even that is test data leakage, and this happens very often in academic settings. Because in academic benchmarks, test data is there. I mean, in an ideal world, you should not be looking at test data, but imagine a situation, right? Where you are a grad student working on a new algorithm. You get your new algorithm. Do you fix your algorithm and just test on test data and whatever accuracy you get, you stop there? Nobody does that, no? So what do people do? If the accuracy is bad, get back and tweak your algorithm and then go back. This is actually wrong, this is test data leakage. So in an ideal world, the training or the ERM should have no information about the test data, even at the level of setting hyperparameters. That's an ideal situation, yeah. That's why you have the validation data. Look at the validation data, do whatever, even validation data you don't train on validation data, set your hyperparameters on validation data and then freeze your model and then release it, yeah. Validation data, that's exactly why you have validation data. No, no, make no mistake. Training data is on which you solve the ERM. So validation data is the one that you use to tweak your algorithm, hyperparameters. You don't train on validation data. So you don't solve ERM on validation data, you only do ERM on training data. Change your hyperparameters looking on validation data, that's it. Change it, that's also a hyperparameter. You can use your validation data to do anything that you want, right? Just don't use the data upon which you report your final performance metrics on. That's called test data, no? So basically all I am trying to say is you have multiple samples of your data set. Use one to solve ERM, use one to set your hyperparameters. The one upon which you show your final numbers, don't use it for anything, okay, in the process of ERM. That is the golden standard, okay. Welcome, yeah. Go on, go on. For the empirical risk, not necessarily. Yeah, the only thing that happens is we are assuming that with the question is does the treatment change if you are looking at empirical risk, right? It does not. The only thing that we assume is that asymptotically true risk goes to empirical risk. So this practical behavior that I just showed you right now is for the empirical case where we have finite samples. If you have infinite samples, you can actually make both bias and variance arbitrarily low. But typically, the so-called trade-off that people talk of always happens because that we are operating with small samples and operating with small models. If you try to reduce the bias, the variance sort of increases and the other way. Please note that it's a misnomer that there is a trade-off between bias and variance. There is no trade-off algebraically. Risk just decomposes into these two terms and both of them can be made arbitrarily low if you design your hypothesis well, and today's ML methodologies are actually doing it by constructing a very large classifiers or very large hypothesis with large amounts of data, okay. But typically what happens is that if you have small samples and classifiers that have lesser parameters, there's a tension between these two terms. It's only an empirical observation, it has nothing to do with theory, yeah. Good question. The question is, suppose we change the loss to squared error from squared error to L1, do we get a closed form expression? We do. There's a paper that does it for cross entropy. You can search it. You can look for that. People have done this for multiple kinds of loss functions. Similar behavior is seen across different loss functions. Good question. The question is there a possibility where the error on training data set can increase? It can. See, suppose you are doing gradient descent using some hypothesis on training data, right? There's no guarantee that by increasing the parameter should decrease the training error. So the designer has to ensure that the models are chosen in such a way that you reach least training error. That's why I told you, start by overfitting. Okay. In practice, what happens is that if you over parameterize, see, let's think about it. No, worst case, suppose you have your model to have as many parameters as there are data points in your training data, then you should be able to achieve 100% accuracy, because all it has to learn is to assign one parameter to one data point. You understand what I'm saying? Suppose you have 1000 data points in your data set and your hypothesis has 1000 parameters. All it has to do is associate one number with one data point, that's it, that gives you 100% training accuracy. So a designer has to always ensure that your model at least gets 100% training accuracy. It may be a very bad model, right? It may be a overfit model, but you should at least overfit. When would the training error increase is when, if you have made your model, let's say underparameterized, and it does not even have a chance to remember the scene data, that's when the error keeps increasing. That can happen. But you'll have to, that's what training is all about. You design your classifier in such a way that training accuracy keeps increasing as you move on. In the next class, I'll tell you more practical ways of doing it when we talk of regularizers, but yeah, so that's how you do it. Question? Good question. The question is, for generative models, what is test data? You'll have to wait till my next course. Yeah, so the thing is the following, right? What is done is that you keep aside some samples. The actual question that you should be asking is, okay, test data is actually some other samples from the underlying distribution that you are trying to sample from. The question that you should be asking is, what are the metrics? Data can always be obtained. The question is, what are the metrics? The metrics are, there are different ones. There is something called Fletcher's inception distance. There are some human evaluation metrics and so on. Suppose you are looking at, there is one very famous data set that we always work on, it's called SWE-bench. With software engineering tasks, a lot of tasks, right? So there you have verifiable metrics, right? How many test cases that it has completed, that's a metric. You can always do that. Data is always coming from the underlying distribution that you are trying to generate from. Data is not the issue. The question that should be asking is, how do you define accuracy when you don't have labels? You can always, right, because we saw labels as one other dimension of data, you can always define some metrics that way. Yeah. Okay, so thank you. This is all about this class. So next class we will look at how to increase the bias of models in the setting of regularization. See you. Thank you.